Today we are going to learn how to use the MATLAB to design the state feedback controller. So this is the example 2-2 in our lecture notes this morning. So we can see here that I rewrite the question. So we have the open loop transfer functions, and the question required us to design a phase variable feedback gains to yield the 5% overshoot and a peak time of 0.3 seconds. So first of all, let us get this matrix, and the state space must be in the phase variable state space. Okay, so let's type these equations. So we have the 100 multiply with our system is sorry, we have 100s plus 10, right? So we have the 100, then this one is the 1, and this one is the 10. Okay, so then because it's in the polynomial, so then we have the then g is it's not in the poly, so we have to make it to the polynomial. Put in the factor is a 0, minus 3, and minus 12. Minus 3, minus 12, yes. So then our GS is transfer function. We use the transfer function command, so we can get the transfer function. Okay, let's run our script. So yeah, this is what we should have, the transfer functions. Then okay, so now the step 1, I think we need to get this in the what is that, the phase. Okay, now we obtain phase variable state space. Okay, so what we can do is we try to get the AP. So from here, because it's not yet in the state space, so we try to get this in the state space. So if we want the state space, we can use the command transfer function to state space, this command. Okay, so what I want, because we know that if we use this command, we will get the canonical form. So canonical form, I use the C to represent it. And here we can write our transfer function, numerator G and numerator G. Okay, so let's say I run this, then okay, so then because I have this semicolon with me, so I couldn't see the answer. Anyhow, I can type here and see this is my A state space, this is my B state space, but in the canonical form. It's yet to be in the phase variable form, so you can check everything. This is 0. So what I want to do is will transform this to the phase variable form. So I would like to use the P to represent the phase variable form. So as we learn is we have to invert. Okay, sorry. So before that, I need to transformation. Okay, show you the transformation matrix. Transformation matrix. So I would like to space so to see you. This is okay. So P equals to, because I have 3 by 3, so I need to write them in the 3 by 3. And then is the 0, 1, 0, and then is the 1, 0, 0. Okay, because I need to get it in the this one. So first I need to get the AP. Okay, AP equals to, we invert this transformation matrix, for the controller canonical to phase variable form. So I will do for the A first, and then the equation is multiply my AC and then multiply with my P. This is the formula you can easily get from the new textbook. So the BP in the phase variable is the we have to invert in P, the matrix, and then we multiply with our controller canonical form, and CP equals to CC multiply my P. Oops. Multiply my P, and then dP actually is same as the dC. Okay, so as I put all these semicolon, for sure you couldn't see them. Oh, sorry, I forgot to run this P. Okay, so then I run again. You can easily to use the keyboard to run the script as you want. So the AP now, you see what is the difference? Okay, you see I have make it to the phase variable form now compared to the controller canonical form previously. Okay, because what we learned in the class is we design the step feedback is based on the phase variable form, and now we are required to get the phase feedback gain. Okay, so so what is I have to do is now the matrix is ready. So we back to what we learned in the class, the solution. I go to the step 1. So what is my step 1 is obtain the desired characteristic equations, right? Then okay, I know that's the overshoot. I use the post. You can anything you want with the OS and so on is fine. So my post is 5%, and my my peak time is 0.3. Okay, so now I need to calculate required damping ratio. Okay, so this is we just type the formula. Okay, we want to get the zeta, right? So we know the formula to get the zeta is on the top is negative log, right? So this one is the post 100. Okay, and then divide by square root. Okay, square root of what? Square root of the pi square, and then pass ln what is the 5 post, my post over 100. Okay, and then for this I need to okay, so then my omega n based on the TP formula, so I can use this one TP. Okay, multiply with the square root of 1 minus zeta square. Okay, so let's see, maybe if we miss some of the brackets, perhaps it will tell us later. So let's run this. Alright, so as what we have calculated in the class, zeta is 0.69, omega n is 14.47 seconds. Radian per second. So now we have to get the equations, right? We yet to done the equations, so now we need to produce a second order system that meets the transient requirement. Okay, so well, I can use the ORD ordinary to the second order. You can see what is that. Okay, let's say ORD 2. Okay, 2. So then you can see what is this. So it's generate continuous second order system. So you can use this already2 command to return the state space to the equations, right? So you can use either one, either you want the state space or you want to use this. So, but both, remember, you use omega n and the z. Okay, so the sequence also must follow what they decided, which is omega n come first. So if I use this, because now what I need is